Hello everyone, my name is Kylie. I'm a researcher from NEC Labs of America. So today I will introduce our work about source-free video domain adaptation with spatial, temporal, and historical consistency learning. This work is joint with Deep Patel, Eric Cruz, and Martin Renqiang Min. So here is an overview of our work. We studied the problem of adapting a pre-trained source action recognition model to target domain using unlabeled videos. We proposed the method which aims to adapt the source model by encouraging it to surpass various factors that cause domain shift with three types of consistency learning techniques. Here is our model. We will introduce the details. The result is that we achieve the best performance on various adaptation settings, including closed set, open set, partial set, and black box domain adaptation. This is the details. So the problem is that we want to learn an adaptive action recognition model in two steps. In the first step, we learn an action recognition model from labeled source data in a standard way. In the second step, we adapt this learned source model using unlabeled targeted data. So we can see that we have a source model, which is learned using labeled data, labeled source data. We want to adapt this model to the customer use cases using their unlabeled customer data. And then we want to get a customized model. So the benefit is that in this way, we can protect the labeled source data from being disclosed to the public, which in this way we can protect the privacy. However, this brings some challenge because during the adaptation process, we have no reliable supervision signal at all, so which makes the source model being very vulnerable during the adaptation process. So the motivation of our proposed method is that we assume the video of the same action category are drawn from the same low-dimensional space, regardless spatial temporal variation in the high-dimensional space that cause domain shift. For example, so we can see that this is the original video. We can see that this video and this video have some kind of variations with respect to this video, but they all belongs to the same types of video in a low dimensional space. So based on this assumption, we just trying to we simulate the spatial and temporal variations with the target video and encourage our source model to surpass these variations. In this way, we can achieve like adaptation. So this is the underlying intuitions behind our method. Then is our details. So here is an illustration. We our framework. In the first step, we learn the source model. In the second step, we adapted this model using unlabeled targeted videos. So so we propose three types of consistency learning techniques. The first one is spatial consistency learning. So for each unlabeled targeted video or keyframe, we apply spatial augmentation on each frame and encourage spatial consistency. So we apply spatial augmentation simply by doing interpolation on each frame, and then we encourage the spatial consistency. We can see that. So this is the spatially augmented video, and this is original video. We use KL divergence to enforce the spatial consistency. Similarly, we do it on the temporal dimension. So we apply temporal augmentation on the original image by randomly dropping a frame, dropping some frames and on the video, and then we encourage the temporal consistency. Further, we encourage historical consistency, which aims to aims to require a prediction consistency with a video clip to be consistent with another clip sampled from the same video but with different frames. So it's more like we want to encourage like the prediction to be consistent for different combination of frames from the same video. We similarly we use KL divergence to enforce the consistency, and we propose to use a memory bank to storage the early predictions for every video. So in this way, we just need to record the early predictions to calculate the loss. So the final learning objective is a combination of the above consistency losses plus the information maximization loss, which aims to encourage individual confident and global diverse predictions. So our method can be extended to can be applied and extended to various adaptation scenarios, including the closed set. This is the standard set. We can see that our method achieved the best performance on these 3 benchmarks. And our method can also extend to the open set, partial set, and the black box adaptations. So we can see that our method also achieved the best performance on these settings. Here the ablation study, this is the full model. We can see that our method will have performance dropped if we remove these consistency techniques, including spatial, temporal, and historical. Here is the t-SNE visualization of the learned feature. Before the adaptation, we can see that there are some overlaps of data of different class, but after applying our method, the cluster shows better clustering structure. So here is the summary and conclusion. So we propose a method which extensively utilizes various video consistency techniques to address the source-free video domain adaptation problem, including spatial consistency, temporal consistency, and historical consistency. And we extend our method to address various source-free video domain adaptation settings, including partial set, open set, and black box model adaptation problems. And in all these settings, our method achieved the state-of-the-art performance on all these tasks and data sets. Thank you very much.